We've talked in the past about casts in C-style notation, where you have a data type inside parentheses that you use to convert the data type of some expression. In Lecture 8, we're going to take a deeper look at type conversion methods in C++, and we're also going to take a look at what's called runtime type identification, which has to do with figuring out on the fly what actual derived kind of object, a pointer or a reference to a base class object, is really pointing to or really referring to. You can request an explicit type conversion in C++ using the old-fashioned C language style typecasts. There's also a slightly improved function-like type conversion that the C++ language provided early on. In more recent versions of C++, there are 4 named type conversions that you should use in preference to the C-style typecasts or C++ function-like typecasts. And in C++ 11, construction using curly braces was added to the language. So this is unfortunate that we have several generations of notation for performing explicit type conversions. It would be nice if the older styles had been thrown out of the language when the newer styles were introduced, but of course that would have ruined the backward compatibility of the language. So here on slide 3 is how you do a C language style typecast. And we've done this before. You put a data type name inside of parentheses, and you put that in front of an expression. Whatever the type of the expression is, it will be forced to be converted to the data type name in parentheses. Now, C-style casts are completely unsafe. When you use a cast, you are saying to the compiler, "Hey compiler, I'm smart, do what I say, and don't complain." And so the compiler will not do any error checking. The compiler will just do what you tell it to do. Here on slide 4 are several different ways of using C-style typecasts. Here we have an int value of 2, and we would like to do floating point double precision arithmetic to evaluate this multiplication and division. So one way of accomplishing that is to force the 2 to be treated as a double. That will cause the multiplication to be done in double precision and also the division to be done in double precision. And we end up with 3.333, etc. as our double result. As another example, here I have an int value written in hexadecimal. Perhaps my documentation for my computer tells me that there is a serial port, some kind of input-output port, from which I can read data and to which I can write data at a particular location in memory, specifically at this location hex 0FFA68BC. Well, it would be convenient for me to have some kind of I/O port class that describes what all the bits and bytes are in this I/O port hardware device in my computer. And so I can set up that class or that struct, and then I can create a pointer to an I/O port. Here the name of the pointer is PIO, and I can force PIO to contain that integer address cast to a pointer to an I/O port. Now in this case the compiler will not actually change the value in any way. The value is still going to be the int that you wrote down as a constant, but it will allow you to just take that integer value and shove it into a pointer, so now you can interact with whatever is at that address through this PIO pointer. Another thing that C-style casts can be used for is to get rid of constness, which is almost never a good idea, but a cast will allow you to do this. Here I have p set up as a pointer to a char const, specifically initialized with the address of the little h in the string literal hello. So the string literal hello is going to be stored in the static data area. That's 6 characters, HELLO, and a null character. And p is going to be initialized with the address of the little h. Now, string literals in static data are intended to be const. Maybe your compiler will allow you to change what's in a string literal, or maybe not. If you want to try to change what's in the string literal, you can use this cast, open paren, char star, close paren, in front of the pointer to say, all right, I know I have this pointer to a character const, but I want to treat it as a pointer to a char that is not const, And then I will use the star to do a dereference or an indirection on that pointer and assign a little j into that location. Now, depending on your compiler, depending on your system, maybe that will store a little j in place of the little h. Maybe that assignment will simply be ignored. Maybe that assignment will cause your program to crash. Since what we're using the cast for here is an illegal thing, namely eliminating the constness of a const, you will get what you deserve on your system. Yet another thing we can do is take a base class pointer. Here I've got PE set up as a pointer to an employee, and I can force that pointer to be treated as a pointer to a derived class object. So here I'm taking my pointer to employee PE, and I'm forcing that to be treated as a pointer to a manager, which I'm storing in this variable PM. Now, maybe this will work. If Bill is actually a manager, then I am allowed to take the address of Bill and store that pointer to manager into a pointer to employee variable. And I would also be able to take that pointer to employee and convert that into a pointer to manager, and everything would be fine. But if Bill is not really a manager, and now I try to do something with PM, like PM arrow get budget to get the budget of this manager, if Bill is not really a manager, I'm just going to get some kind of garbage, whatever stuff is sitting around in memory after the employee data members that Bill actually contains. Okay, so C-style casts are very powerful, totally unsafe. If you use them and you know what you're doing, you'll be fine. If you don't know what you're doing, mysterious things are going to happen, your program is going to crash, you will deserve what you get. Now, when Strustrup developed the first version of C++, he felt that the notation for C-style casts was ugly, and so what he permitted was function-like casts to accomplish the same purpose. For example, if I want to treat 2 as a double, then in the function style of type conversion, I would use the name double as though it were a function with integer 2 as my argument, and that will force the integer 2 to be treated as a double precision 2.0, and so forth. Now, frankly, the function-like type conversions are no safer than the C-style typecasts, and furthermore, they're a little bit harder to use, because let's suppose that I wanted to treat this integer value, hex 0f-fa68bc, as a pointer to an I/O port. Well, pointer to I/O port is not a name, so I first have to create a name, which I'll call I/O port pointer, using typedef. So now I can use that name in the next statement as though it were a function to convert that integer value into an I/O port pointer, which is simply an alternate name for pointer to I/O port. That works fine. It allows me to use the function style type conversion from the early days of C++, but notice that I haven't gained any safety, and I've had to write 2 lines of code now in using a typedef rather than the 1 line of code that I wrote over here on slide 4 using the C-style typecast. The named type conversions that we're going to take a look at here starting on slide 6 with Constcast were introduced as a somewhat safer and somewhat more clear method for standardizing the 4 different uses of casts that we've illustrated back on slide 4 with our C-style casts. Now, it's important to understand that these are not really safe. You can still do stupid things using these casts, but you will get a little better support from the compiler. And of course, it's much easier in your editor or in your integrated development environment to do a search for const_cast as opposed to trying to do a search for a pair of parentheses, because of course parentheses are all over the place in C++ code.